All right, spectral dependence. So as I've said now, a real surface has emissivity and absorptivity characteristics that relate to properties of the surface, right? The chemical composition of the surface. So here what I've got is pulled this plot of some common surfaces. So if you're doing like trying to compute the reflectivity of the Earth, they call that albedo, right? If you try to compute the reflectivity of the Earth, you want to know the emissive or reflective properties of common substances. So water, ice, snow, desert. So these satellite images that are trying to figure out, like, is this a cloud? Is this snow or whatever it is? They can look at these signatures and figure out, okay, was this sand? Was this ice? And so on. And it's not just by looking at the total like color, it's looking at the spectral dependence of these different surfaces. So what you see here is like some pretty significant variation. So for example, like sand, here we see the desert, this green line here. You see some kind of big characteristic dips in the emissivity as a function of wavelength at these certain places. Likewise for ice, you can see maybe at the lower wavelengths you have lower emissivity. So there's these kind of characteristics. So you might wonder like where this comes from, where it arises from. So to tell you where kind of like these properties, how they originate, what I'm showing here on the right is, this is like a spectral map of emission from individual elements. So it's really hard to see. Let me just zoom in a little bit, maybe. Come on. So it's up on the top here, we have hydrogen. So what this is saying is like as a function of wave number, it's a proxy for wavelength. If you increase the wave number of light that's hitting hydrogen, eventually it's going to start resonating or emitting. And it does it at these specific wavelengths. Right? So at one particular wavelength, and then there's a gap. And then another wavelength and another wavelength. So individual elements or individual molecules only emit at certain specific wavelengths. And it's basically because there's only certain energy states that are available to a given atom or a given molecule. So hydrogen's really simple. You only have a few energy states. Remember back to like your chemistry or physics, right? There's like certain shells that electrons can exist in for these things. So the smaller the number of energy states that are available, the smaller the available emitting states. And the smaller the available emitting states, the smaller the number of absorbing states, right? And emissivity is equal to absorptivity. So what you see here is like hydrogen is basically limited. As you start going up, helium, you get more states, right? It's a more complex atom. Nitrogen is even more complex, oxygen, right? And so you start seeing these patterns that emerge. If you go down to other things, neon, xenon, mercury, right, you just sort of see how they all play out. So this is kind of interesting, but this is where the emissive properties arise from. As you go to like things like sand or water or whatever, these are big, solid, complex systems, and not only do you have to deal with electron states, but you have to deal with like vibrations in lattices and interactions and things. And so what starts as a really discrete pattern actually fills in to be like a more continuous black body spectrum, all right? One other thing I'm going to say about this, which I think is really interesting, but I didn't have a graphic for it, but has anybody ever seen like a spectral image of light from the sun or from a star? You guys all, have you seen that before? Right, it's like you look at a chart like this, and instead of like if you look at the sun, you'd expect to see a black body curve. Right? But it's not a black body curve. There's little gaps in it, right? There's gaps in places where there are no elements in the sun that emit at that specific band. So there's just a gap, right? And that's actually how you can tell what the composition of a star is, or the sun in this case, or really anything you're looking at, is you look at the light that's emitted from it, and it will emit at certain bands, and it's like a fingerprint, right? You can see from that fingerprint what the composition is. So heat transfer is not just not just for moving energy around, it's also for kind of identifying composition of materials as well. All right.